Hello students, let us start off with the topic of binomial theorem. Before we directly jump into this topic, let us quickly refresh some of the previous concepts and few formulae that we would need in this topic. Firstly, collect the factorial notation that you must have done in the topic of permutations and combinations. If not, here it is. For any natural number n, the n factorial as shown here by the symbol n and exclamation mark is defined as the product of all the natural numbers from 1 up to that number n itself. Okay, so that's the definition of n factorial. Now although here we say that n should be a natural number, there is a special case of 0 factorial which is an exception, and we have to remember it as 1. Okay, so the 0 factorial is specially defined to be equal to 1. Now after this we have to quickly recollect the formula for NCR, okay, which stands for the number of ways in which we can choose or select R objects out of n objects. Okay, so this also you must have done in the topic of combinations, and as per the formula, NCR is given as n factorial divided by R factorial into n minus R the whole factorial, right? And then we also use one important property of the combinations, that is NCR is same as NC n minus R, simply because when we say that 10C2, that means number of ways of selecting 2 objects from 10 objects, that is same as number of ways of rejecting the remaining 8 objects, right? So therefore this is one simple application. We'll be seeing this particular property in binomial theorem also as we move ahead. Alright, let's go ahead. Alright, now to set the context for binomial theorem, what it is and what it is for, let us recollect what we learned in the school time for expansion of a plus b the whole square, right? All of us know how to expand it. It is a square plus 2ab plus b square, correct? In fact, we also know how to expand a plus b the whole cube, and that is a cube plus 3a square b plus 3ab square plus b cube, isn't it? Alright, now here in this particular left hand side, the expression a plus b is called as a binomial because it is an expression containing 2 terms, therefore it's called as a binomial, and the power to which it is raised is called as the index, as we know. Now the question comes, we know the formula only for the expansion of square and cube of the binomial. What if we want to find out a plus b whole raised to 4 or even higher powers? Is it like we will be simply taking a plus b the whole cube and then multiply by a plus b? That would be a very tedious thing. So this is where the binomial theorem comes into picture, and it is going to give us a direct formula for expanding a plus b whole raised to n, okay, where n can be any number, but we will see for different types of n we have different formulae. So first of all, we will be focusing only on a plus b raised to n, where n is a natural number or a positive integer, in other words. Okay. Now once again, looking closely at the pattern that we have, let us rewrite starting with a plus b raised to 1. Alright, we know that of course that is equal to nothing but a plus b, not a big deal in that. But here what I'm going to do is I'm going to write the coefficients of the individual terms specifically. Okay, so here a plus b means 1a plus 1b, right? Good. Let's move ahead with a plus b the whole square. This we know as a square plus 2ab plus b square. So here the coefficients of a square and b square are 1 and 1 respectively. Then moving on, we have a plus b the whole cube, that is a cube plus 3a square b. I'll write the coefficients later in different colors so that it is easy to understand and learn how the coefficients are changing. 1, 3, 3, and once again 1, and all the terms added. So now slowly we are going to discover a nice pattern among these coefficients as well as the powers of the individual terms. If you observe in all of these expansions, as we go from left to right, the power of A reduces from highest to 0 and power of B increases from 0 to highest, and highest power is the same as the power to which the binomial is raised. So in first case it was power 1, so therefore we started off with A raised to 1, and in the second term A has vanished, so we can visualize that as A raised to 0. Similarly, in the first term B did not have any power, so it was B raised to 0, and in the second term B raised to 1 has appeared. Similarly, we will see that in the A plus B square it was A square, then A, and then A has vanished, and in case of B there was no B term in the first, then B has appeared, and then you have B square. And same thing now you can observe is happening in case of the expansion of the cube of A plus B also. So that is first important observation. The second observation is about the coefficients. That is, if you see the coefficients were 1 and 1 in the first case, then it was 1, 2, 1, and then 1, 3, 3, 1. Now let us think what are these numbers and can we find out some pattern. So the pattern is like this. The number 1 in the first expansion is obtained as 1C0, and the second one is obtained as 1C1. Similarly, the numbers 1, 2 and 1, the coefficients in A plus B raised to 2 are obtained as 2C0, because you see that 2C0 is nothing but 1, then 2 is nothing but 2C1, and the last one is nothing but 2C2. I think now you can see what is happening. Similarly, now we can turn our attention to the coefficients in the expansion of the cube also. The coefficients are 1, 3, 3, 1, and since now here the index is 3, they must be related with the number 3, and yes, it is 3C0, 3C1, 3C2 and 3C3. Now here the picture is completely clear. What is happening is the individual coefficients are based on the index to which we are raising the binomial, and the lower numbers are successively starting from 0 and going up to the highest number, which is same as the degree to which we are raising that binomial. So therefore, now suppose if we want to generalize and get an expression for A plus B whole raised to n, where n is a natural number, clearly we can get a pattern, and that is what is given on the next slide, and that is the statement of the binomial theorem. So here it is. For a positive integral index, that is when n is a natural number, we have A plus B whole raised to n given by, you see we start off with nc0 and the highest power of A, that is A raised to n. Then the next coefficient is nc1, the power of A is reduced, so n becomes n minus 1, and power of B now becomes 1, so the term in B has now appeared. Then moving on, we have nc2, power of A reduces by 1, whereas power of B increases by 1, so B becomes B square and A reduces to A raised to n minus 2, and so on till the last term would be, of course the last coefficient would be ncn, and B will be raised to the highest power n, and there will not be any A term visible in the last term. So this is the statement for binomial theorem for positive integral index. Now based on this we can deduce a lot of things. The first immediate deduction is, instead of plus B, if we have minus B in the binomial, then we can see that wherever we have odd powers of B, so B raised to 1, then in the next term we will have nc3 A raised to n minus 3 into B cube. So here whenever we have odd powers of B, all those terms will become negative. So therefore we have alternate terms, positive and negative, in the expansion of A minus B raised to n. So here are a couple of terms I'm writing for our reference. And so on. Now how do we know what is the sign of the last term, because it depends on whether n is even or odd. Okay, so in that case what do we do is, if n is even, we want the last term to be positive, correct, and if n is odd, then we want the last term to be negative. So for this we attach a small expression which is -1 raised to n, which always helps us to put a correct sign based on whether n is even or odd, and we will complete the last term as ncn b raised to n. Now here you can see if n is odd, then we will actually get the final term as negative, the coefficient will be negative. If n is even, then it will be positive. Alright, so this is the deduction of the binomial theorem based on the original formula.